As you can see from the previous two videos, we're going to be adding a lot of things up. We're going to have these big, long sums. So it's going to behoove us to find some notation that sort of shortens what we have to write. And so this is what's called summation notation. It looks like this. You may have seen it before. I don't know. Sometimes people have by the time they get here, and sometimes they haven't. In general, it might look something like this. I equals 1. This is the capital Greek letter sigma for sum. I is what's the index of the sum, and then you give a starting value and an ending value. And then in here, this is essentially a function. We're writing the I as a subscript, but essentially we're saying I may have a list of values or a function that's called A, and you plug in different values of I and you get different outputs. But the idea here is that this one thing means take the first value of I and plug it in. Well, it just looks like an A1 at the moment. Plug the next value of I, and we're going by steps of 1. So I would be 2. So plug a 2 in for I, that would be A2. And then plug a 3 in, A3, and so on, up till the last one, which in this case is AN. Okay? It's a sum of all those numbers all the way up to n. Okay? Notice that this is particularly nice because something that looks like this, let's do the sum I equals 1 to n of f of x I star times delta x, right? That what this means is take the 1 and plug it in for I. This is f of x1 star times delta x plus, then do the same thing again with a 2 plugged in, f of x2 star times delta x plus, keep going all the way to the last one, f x n star delta x. And this is what we had in the last video for the summation that estimates the area under the function from A to B. Okay. Shorthand notation for big long sums is going to help us out. Let me do just one example where it's not an area calculation, but you might use the I in different ways. So let's just suppose I have some numbers up here where I know that A1 is equal to 7 and A2 is equal to 9 and A3 is equal to 4 and A4 is equal to -2. Right? That somehow I have this information. And I want to look at the sum I equals 1 to 4 of I times AI. Right? This means, right, use the 1, plug it in every place you see the I. This is 1 times A1. Plus, now do it with a 2 plugged in, 2 times A2. I don't know why I put that in parentheses, but I did. Plus, now do it with a 3 plugged in, 3 times A3. Do it with a 4 plugged in, 4 times A4. Right? That in this expression right here, I is being used in two ways. I is being used as a number to multiply by, and I is being used in a subscript, which references some other sequence of numbers, A1, A2, A3, and A4, that we can bring into the picture now. So this is 1 times 7, plus 2 times A2, which is 9, plus 3 times A3, which is 4, plus 4 times A2, which is -2, for a grand total of 7. Well, I guess I'm not doing the grand total yet. 7 plus 18 plus 12 minus 8 for now a grand total of 12, 22, 29, I think. 29, say it without the question mark. Right. This notation, you're going to run the index I from whatever starting value you give here. It's usually 1 or 0, but you can start it at anything, up to the ending value, and you go in steps of 1. So you plug a 1 in every place you see an I, you plug a 2 in every place you see an I, a 3, a 4, all the way up to your last value, and you add up all those results. with the 1 plugged in, with the 2 plugged in, with the 3 plugged in, and you get some number. We will be using this time and again to be calculating areas of this sort. These are the summations we're going to be looking at.